That is actually intentionally spelled wrong. It's an acronym that nobody remembers anymore. Harry was good to point out, he actually made an image that looks like Led Zeppelin, but with this, you know, it really looks pretty cool. You have to send me that.
Yeah, I do, yeah.
It's funded by the DOE, it's a project. We're projected to start taking data in 2020, and we're hoping we think we can get a 100-fold increase in sensitivity over loss. So this is what it would look like. It's 10 tons of liquid xenon. Now to put that in perspective, in the industry, the world produces 40 tons of liquid xenon every year. So we're taking a quarter of the world's annual xenon production. We're going to have a lot of methods of reducing background. Some veto detectors that can tell us when a particle entered. And in particular, this big green thing, which is the responsibility of Harry's group here in Santa Barbara. I was going to put some more photos on here, but I didn't get a chance. I wanted to, right. So there's also some innovations like we do all the cooling outside of the water tank to xenon as a cryogenic liquid. And here's where we project, here's that lux sensitivity curve. And we think we can get down here. Now, what's all this yellow stuff below that? Well, there are astrophysical sources of neutrinos. We know neutrinos can interact with atomic nuclei as well. And at some point, that's going to become an irreducible background. So we're getting really close, we think, to this, what we call neutrino floor with LZ. Okay, so where's the field going? Well, the WIP was supposed to be a miracle, but is that really the case? What would we expect for a weakly interacting massive particle? Well, if it's a weak interaction, that suggests it interacts with the Z boson. It's one of the mediators of the weak interaction. But what would the cross-section be if it talked to normal matter with the Z bosons? It would be up there. For a particle of the weak scale, that was excluded a really long time ago. Right now, what we're probing is interactions that are mediated by the Higgs. Okay, and that's what dominates this blob here. So, is the WIMP really a miracle? We kind of excluded the WIMP as it was originally formulated already. Okay. So, people are asking instead of pushing down further here, it just gets more and more costly. Remember that thermal relic range was from 100 TeV down to tens of keV, and that's 1 GeV. So there's a lot of range over here that nobody's probed. Okay. All that stuff is allowed, even further below, that's 1 MeV, below that is allowed for a very reasonable dark matter candidate, something that was produced just because the universe was hot at one time. Okay. So, what I'll leave you with is to say that this range that's completely untested and fairly well motivated, so far we've only just taken baby steps into probing dark matter in this regime. We don't really have, the current technology is not really well suited to search for dark matter here. And right now new technologies are being developed. It's a really exciting time to be an experimentalist because to do science we have to invent new detector technologies. And instead of going over time, what I'm going to do is just give a plug. I'm giving you a seminar tomorrow, and the seminar is going to be just on the topic of exploring this regime. How do we think we can do it? And what are some things we're going to try to get there? So, and with that, I'll just finish.
We have time for some questions, and Aaron, you should pick people. I'll just stand here and thank people.
Oh, there are. Oh, yeah.
So if it turns out that dark matter is an axion, then what is causing the WIMP miracle? Like if there's not a WIMP, like how do you explain?
If there's not a WIMP, there's not a miracle. But this problem with electroweak symmetry, it's not just dark matter that's having this problem. Because the theories that have been proposed to explain this probably should have shown up in colliders by now as well. And they haven't. In fact, the general notion is that above, like let's say, an energy of a TeV, there would be new physics that would show up that would explain why the Higgs mass is not divergent. But that scale for new physics has been pushed up and up by the LHC, and I'm not actually sure what it is now. It's like 10 TeV or something?
It's about 1 TeV for the mass, like
Oh, okay,
neutrinos,
right.
yeah, 1 or 2.
Yeah. So it's getting to the point where it's difficult to explain that. So this is a problem not only with dark matter, but also with colliders. So we don't know.
But I guess we know that there's evidence of dark matter.
Yeah.
There's a separation. There's a thermal separation with some cross section.
Oh, no, we don't know that. That's just a proposal for, we see that if a particle has those properties and it existed in the early universe, that's what would have happened. But we don't know that such a particle exists. That would be required. Yeah.
I have a question about, I guess, the astrophysical evidence. So
Yeah.
tell me if this story is right.
Okay.
We have bullet cluster type things that are going through each other and getting all their baryonic matter stripped off.
Yeah.
So those clusters are super, super dark, right? They're way darker than the non-collided cluster because, so the virial theorem says they should look really different, right? Because they have, like, the Milky Way is 80% dark, but those post-collision clusters should be 99% dark. And is there evidence of that? Are those clusters super virial? Like where your mouse?
Yeah, I don't know that, I haven't seen a few people have tried to examine the dynamics. So actually what happens, there's another component of the galaxy cluster, which is the galaxies themselves. And they're actually far enough apart that when you just run the simulations of two galaxy clusters merging like this or interacting, the galaxies generally just pass right through each other. And so, the galaxies themselves are right over here as well. Okay. But I don't know if people, and over here, I don't know if people have actually looked at the RMS velocities, the relative velocities of the galaxies in here. It's not, I mean, this is, if we believe dark matter, this is not the dominant mass of the cluster anyways. Okay. There's about 6 times more dark matter in a galaxy cluster than there is baryonic matter.
It's not that dark.
So this is like 1/6 of the mass. So it would be, the change would be, on order of 1/6. That's the scale you expect.
More questions?
What benefits from the James Webb Space Telescope do you foresee?
I don't know, because I don't really know of any theories that predict infrared photons coming out, unless it's there's a light dark matter particle that annihilates to infrared photons. There's a lot of infrared that comes out of other processes. There's probably going to be a lot of background. I actually never heard of somebody talking about infrared telescopes looking for dark matter. Maybe dark matter heats up some region of part of a galaxy, but a lot of other things can do that too. So I don't know, and I get the sense there's not really a lot of actually looking at it.
There's also Andrew over here.
What are the cross-sectional limits on winds at the lower energy scales, and what experiments are those coming from, or observations?
Cross-sectional limits on the lower masses.
Yeah.
So let me go back down.
Like there's some lines on that wood,
So
on the
here.
second slide.
This one?
Give me a second. Mm-hmm.
This one.
Yes.
Yeah, it's the same. Yeah. So these are. So I mentioned that at some point these liquid detectors took over because they could scale up in mass. Okay. Now the teams working on the crystal detectors that previously were very innovative, they realized that they couldn't keep up because of scalability. So what they decided to do is really focus on pushing to lower and lower energy thresholds. So it turns out that as I go to lower and lower WIP masses, the characteristic scale of the recoil energies from those becomes smaller and smaller. To probe this region of parameter space, you need very low energy thresholds. And so that's what these experiments have done. This is actually CDMS, the thing that, the blue one is the thing that actually Harry and I used to work on. And then the cyan is another low temperature, tens of millikelvin scale small crystal detector. So they use small masses but very low thresholds.
Okay, so my question is,
Yeah.
below that,
Yeah.
what are the limits?
So I didn't. There's like one.
One.
Yeah. There's one, and I'll talk about it tomorrow.
Tell me where I'll
And it requires a different type of detection. You can't really look for nuclear recoils in
So almost certainly involves low temperatures because the energy deposits are so low. That's the simplest. You got to deal with KT gallons. I think. Am I blowing smoke there? Does that sound right?
It's also, if you want to detect something, you need to excite something in your detector material. So the question is, how much energy do you need to excite it? It's a band gap. Liquid xenon, it's about 10 EV. And a semiconductor like silicon is about 1 EV. A superconductor, super pairs is like a milli EV. Give you a sense of,
Yeah, sure.
without giving it,
You got all high, we go.
What's currently the main, most difficult background to deal with for the LZ?
So I can answer this because the way that LZ works, it's a big project for the DOE, and the DOE likes to create what's called boxology. They fill boxes, and there's hierarchies, and everyone's got to have a manager and a subsystem manager. And there's one box, which is the person who's in charge of cleanliness of the detector. Cleanliness means dust. The reason that's important is that dust emits radon. Pull up one other thing here, just to have it. Okay. So this thing I talked about scaling, that only works if the sources of dark matter, or sorry, the sources of background are exterior to your detector. What if you actually have a source of background that's uniformly dissolved in your detector? This doesn't help at all. Radon is a noble gas, like xenon. So dust emits radon. There's some residual amount on any surface, even if you precision clean it and do everything you can. So we care a lot about radon. Okay? And every material just sort of emits radon. This is a natural thing that happens. The floor right now is emitting radon. There's an interesting process where that happens. And we can build an experiment where we try to limit that, but we can't get rid of it. That actually forms the dominant background, will form the dominant background in LZ, is radon.
As you know, Aaron's many talents is he's an expert on all of that.
Wow.
Among your many talents. Yeah. More questions for Aaron?
So you said we can observe to the center of the galaxy, like the gamma rays to like observe the annihilation between the dark matters.
Yeah.
And also you said like locally the density of dark matter is like 3 protons mass per liter.
Yeah.
The first question is like how much denser is it for like center of the galaxy?
Oh, that's it. So that's an open question. I can't answer it because people argue about that. About what's the density in the center.
Okay, so another one is like what's
Look,
this?
Look, yeah.
What is
The-
the
So, no, go ahead. Yeah, sorry.
so what is the minimum annihilation rate so we can observe like the gamma rays from that?
It depends on what else is there. The difficult thing about looking for gamma rays from a complicated environment like the center of a galaxy is that if you see some source, okay, is it dark matter? Maybe. Could it be something not a new process? Like, so here, for example, this is the Hess Observatory looking toward the galactic center and looking at gamma rays. This is understood as being caused by accelerated charged particles. It's a crazy environment, hitting a gas cloud. Okay, so we think we understand this, or they think they understand this. But there could be some. It's a complicated environment. So detection of a dark matter particle with this method is difficult. You may see something, but it will be difficult to convince your colleagues and the community that you understand the environment well enough to know that what you're seeing is not already known in physics. You have another question, or did I? Okay.
Well, maybe one more if there's someone.
Yeah, sure. Okay, you highlighted axions and WIMPs.
Yeah.
Okay, is there a third dark horse candidate?
Oh, there's like 10 million.
Well, okay, what's number 3 on the list?
Oh, well, okay, let me go back here to this part, this diagram. So, I kind of highlighted that the WIMP is becoming less well motivated. that opens up, in relative sense, other things within the thermal band here to be, in relative terms, equally interesting. Okay. So I don't personally, and other people might disagree, but I don't think really that this range of masses is really that much more well motivated now than any other particular range within what's allowed for thermal masses. In this regime, this is an entirely different thing. These things are really behave differently. There's actually quite a few candidates here. The axon is one. There's also another interesting candidate is inflation sort of excites all degrees of freedom. So tensor fields will get excited, and we would see that as primordial gravitational waves. There's a weird thing that I don't really understand, but you can ask when a field gets excited by inflation, and then what happens to those excitations as the universe expands and cools. They kind of like disperse, except if that field is a vector with a small mass. It tends to propagate, stay cold, and have a rather peaked mass of like 10 to the minus, I think, 14, something like that, eV. So that's a very natural candidate, because all you have to say is that the field exists and automatically, and inflation exists and automatically will be produced. So this dampening of our motivation for the WIMP, that's not reflected in the axion. The axion is still quite well motivated. So there's still quite a bit of open space for the axion that has not been tested yet. It's not so difficult to look for the axion. It's difficult to scan over a large range of masses. So there's still a lot of potential space for the axion to still be there.
Well, let's thank Aaron again.